Hi, my name is Hyan Huang, and I'm going to be talking about our second lab. So in lab 1, we created two charge tapes and found the electric charge of each tape by finding the distance in which one tape began to float above the other. And in lab 1, we did this by treating each tape as a point charge, but in lab 2, we distributed the charge evenly throughout the length of the tape. And basically what this means is that we treated each tape as a line with infinitesimal sections, and each of these sections having their own point charge. And by treating each tape as a line of distributed charge, we were able to create a much more sophisticated and accurate model. And there are some physics principles that we used in lab 1 that we also used in lab 2. And these are the electric field, electric force, and gravitational force formulas. And you can see them right here. And we also use Newton's second law, which means that if acceleration is 0, force is 0. And so when things are in equilibrium, the net force is 0. And that's the case for our tape in this lab. We also use Newton's third law, which means that every action has an equal and opposite reaction, which is used when to say that both pieces of tape exert opposite and equal forces on each other. And so here's the data that I collected. And most of this data is the same as my first lab. And so the length of each tape is 0.2 meters. The mass of each tape is 0.0002 meters. And the distance between the two tapes when one begins to float above the other is 0.025 meters. And here I just show you how I found the charge when I treated each tape as a point charge, and I did that by equaling the gravity force to the electric force, and I got 1.167 times 10 to the negative 8 coulombs. And so now I'm going to be talking about how I created my computational model. And here you can just see my constants, like my k value, which is 9 times 10 to the 9, and gravity, which is 9.81, and also the mass of one tape, which is 0.0002 kilograms, and the estimated net charge on one tape which is 1.167 times 10 to the negative 8. And here I just created a function that calculated the electric field of a point charge. And here, this is a function that creates a line of distributed charge. And so I create a line of charge for my top tape and a line of charge for my bottom tape. And here I just established the scales that I'm going to need to make sure that my arrows, when I run my code, so that they're viewable and that they're not too small or too big. And so here I'm just iterating through each piece of charge, those infinitesimally small charges in my top tape, and trying to find the net electric field on my top tape due to the bottom tape, and the electric force on my top tape due to the bottom tape. And here I'm just creating an arrow for my net electric field on each of those point charges on my top tape, and creating an electric force vector and a gravitational force vector. And so here you can see everything that I coded. And so this collection of red spheres, that's those are the infinitesimally small pieces of charge on my top tape, and the bottom are those infinitesimal pieces of charges on my bottom tape. And those green arrows are going to be my net electric field on my top tape to the bottom tape. And the yellow arrow is the gravitational force, and the white arrow is the electric force. And you can see here that my white arrow, or my electric force, is way smaller than my gravitational force, which is not true or accurate, because they should be equal to each other, because, like I said before, Newton's second law says that the net force has to be 0, so they should be equal and opposite to each other. And so I played around with some numbers until I got a charge that would give me an electric force that was equal to my gravitational force, or almost. They're a little apart, but it's so small that it doesn't matter. And so my charge is 2.582 times 10 to the negative 8. And so some questions I have to answer is, what if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So if I modeled each of my tapes as a single point charge, I would have gotten the same results that I did in my last lab. In my last lab, I got that each tape had a charge of 1.167 times 10 to the negative 8. But in this lab, I got that each tape had a charge of 2.582 times 10 to the negative 8. And why do these estimates differ? Which value is more likely to be closer to the real value? These estimates are different because in this lab, I treated each tape as a line of charge with infinitesimally small section of tape or charge, and that would give me more accurate amounts and positions of the charges, and so obviously the numbers will be different. And the line charge model is way more accurate because it replicates real life, where the charges on the tape aren't all like in the center of the tape, but are instead distributed evenly across its length. And that's it. Thank you for listening.